In algebra, students start with a single equation, with a single variable. You gotta solve for x. A couple years later, usually, they are introduced to the idea of a system of equations, multiple equations with multiple variables. Now you're solving for x and y and z and maybe others. So far in this course, you've been introduced to the idea of a single, isolated differential equation. You want to solve for some function f or y or what have you. Now I make the same exception as with algebra. I can consider a system of differential equations. Multiple equations with multiple variables. Solve for a variety of functions f, g, and h. As with algebra, the idea is that the functions in the system are all related to each other. Instead of just understanding how one population changes over time, I want to understand how two or more interacting populations change over time. Instead of measuring the movement of one particle, one object, I want to understand the movement of multiple objects which interact with each other. This requires multiple functions, and hence multiple equations about those functions and their derivatives. Let me run through the definitions first. A system of differential equations is a set of equations about several functions and their derivatives. The derivative of one function can show up in an equation with a different function. They are mixed together in strange ways. The order of a system is the highest derivative anywhere in the equations. And as with the rest of this course, I'll only introduce first and second order equations. And this chapter will mostly only tackle first order equations. An autonomous equation was one where the independent variable didn't show up. In a system of differential equations, there is still only one independent variable. All of the functions depend on the same variable, usually time. For a system to be autonomous, it just means that every single equation in the system is autonomous. The independent variable, remember that it's one unique independent variable, even though there are many functions. The independent variable doesn't show up anywhere in any of the equations by itself. A linear system is, unsurprisingly, a system where each equation is a linear differential equation. If there are derivatives from different functions, they can be added together and multiplied by coefficients, but there's no other operations. And finally, the linear system is homogeneous if there are no terms that involve the independent variable. That is, anything that's just a function of the independent variable is just zero. And this is more or less equivalent to saying that each equation is by itself a homogeneous linear differential equation. A good part about the definition was linearity. Let me take a minute to talk about this theme again. Roughly speaking, you can divide the theory of differential equations into two categories, linear and nonlinear. The linear category is the easy one, and nonlinear sort of functions as a synonym for difficult. And this theme is even more prominent in systems, where the difference between linear and nonlinear systems is extremely important. We're only going to solve linear systems, but I'll talk a fair bit about nonlinear systems and how they work. Even with nonlinear systems, I'll often look for the closest linear approximation, the best linear version, and I would hope that that might capture enough of the behavior. If it doesn't, I'll say that the important details are in the nonlinear pieces, or in the nonlinearity. And this is essentially bad news. For anyone who wants to use differential equation, it is ideal if the important behavior is in the linear part of the equation. If you have to go to the nonlinearity, you're going to have a mathematically much more difficult situation to manage. That's enough for general introduction. Let me also in this video do some important key examples to show you the flavor of systems. Here's the Lotka-Volterra system. This is a system for an interacting population of predators and prey. P is the prey population, Q is the predator population. We have the derivatives, time derivatives, telling us how the prey is changing and how the predators are changing, and we have these four terms. A is the predator birth rate. That means that by itself, this would just be exponential growth for the prey's birth rate. This would be exponential growth for the preys. But the prey also lose some of their population by predation. So this negative PQ is the product of the two populations. So that measures how many interactions there are. So minus BQ, some percentage of those interactions result in the death of a prey animal. So the prey animal grows, but also loses some amount to predation. The predator only grows because of predation. So this CPQ is a growth rate for the predators due to the fact that they are preying on the prey. So it's the interaction PQ measures how many times the predators and prey see each other. And based on that interaction, that food source allows the predator population to grow. And then the predators have a natural death rate. So there's an in and out of each of these, a growth and a decline, and they're coupled. The P's and Q's are multiplied together. Most importantly, this is a non-linear system. Since P and Q are multiplied together, that's not a linear thing. In a linear system, you're only allowed to add functions together with coefficients. Here, I'm multiplying P and Q. So this is an important example of a non-linear differential equation. This is also one of the starting points of mathematical biology, one of the first historical models that people studied to understand what was going on, and still to this day is a pretty good way of modeling certain predator-prey interactions. Instead of predators and prey, we could have two species competing for a food source. So I have species P and species Q. They're not preying on each other. We don't have predators and prey here, but they both are sharing the same source of food. So they have an influence on each other. These equations start with ordinary exponential growth on the outside. dp dt equals ap. That's what exponential growth looks like. The growth rate is a constant times the current value, and same for Q. But then this is modified, making it smaller. So there's something that's going to temper this growth. So 1 minus tells us that if this was just 1, it would be exponential growth, but I'm going to subtract something. And what I'm going to subtract is the competition and the carrying capacity. So these are two things that can happen in an ecosystem in a mathematical biology model. Carrying capacity is just basically how much the environment can handle. But then I also have the first population plus some coefficient times the second population. That's going to measure how the second population competes with the first. And the same thing here, Q plus BQP is going to measure how P competes with Q and the effect of that on the growth rate of Q. The key idea is that the systems are coupled together. They affect each other. P shows up in the equation for dp dq dt and vice versa. This is again a nonlinear system because if you distribute the P and Q in front of the brackets, you'll get P times P and P times Q. You'll get multiplication of functions, so a nonlinear system for competing species. And finally, another really important and fundamental mathematical biology model. This is the SIR model for infectious disease. SIR refers to 3 portions of a population. S is susceptible, I is infected, and R is recovered. So you've got an infection going through a population. Some portion is not yet infected, but capable of being infected. Often the S's and I's and R's are percentages. So some portion of your population is susceptible, some portion is currently infected, and some portion have recovered. All right, what happens to your susceptibles? Your susceptibles only decline. So I've got a negative growth rate on the susceptibles. And what happens is the interactions, again, I times S, is every interaction between an infected and a susceptible person in your population. Some percentage of those interactions, that's what this coefficient A is measured, is going to result in the infection spreading to a susceptible person. And the fact that they're subtracted here means nicely that they're added here. When we remove them from susceptible, they show up in infected. They become infected. So this AIS, again, is based on the multiplication of I times S, showing the interactions of the two populations. And then these infected, some of them will recover. So minus BI, B is some recovery rate. So some of these infected will be removed from affected and put into recovery. This is a negative coefficient in the infect growth rate. So this is removing from infected, and a positive coefficient in the recovered. And in this system, this is for infections that run through a population, like a seasonal cold. You start with almost everyone being susceptible. The infected grows, and then most of the infected recover. There's no death dynamics. This is suitable for sort of short-term populations where you're not necessarily worrying about the birth and death rates of the population themselves, just how the disease is going through. And this is a lovely model. This is still the basis for many mathematical models of how infectious disease works.